Hello, dear traveler. Welcome back to the Sleepy Circle. Have you ever stood at the ocean's edge and wondered what force moves billions of tons of water twice every single day? Have you ever gazed at the moon in the night sky and felt that ancient pull that has inspired mythology, science, and human exploration for thousands of years? Today, we're exploring one of the most profound relationships in our solar system, a cosmic dance that has shaped the history of life on Earth, influenced the myths and cultures of every civilization, and continues to govern the rhythms of our oceans, our biology, and our planet's very future. Talking about the moon, Earth's closest celestial neighbor, our eternal companion in space. And more specifically, we're diving deep into the physics, the mythology, the mysteries, and the science that explains how this relatively small, rocky body in orbit around us creates the tides that move billions of tons of water twice every single day. Over the next few hours, we're going to explore the moon at a depth most people never experience. The physics that explains how a celestial body 238,900 miles away can move massive amounts of water on Earth's surface twice every day. We'll examine gravity, differential forces, orbital mechanics, tidal locking, energy dissipation, and the relationship between the moon's slow recession and Earth's changing rotation. We'll examine the origin story of our moon, how it came to exist, and why Earth is one of the few planets with such a massive satellite. We'll trace the mythological journey of lunar deities across cultures, from the Greek Selene to the Chinese Chang'e to the Hindu Chandra. We'll explore Apollo, the sun god, and his complex relationship with his twin sister, Artemis, goddess of the moon. The moon isn't simply a distant object in the night sky. It's an active participant in the Earth system. It's a partner in an intricate dance that affects everything from ocean currents to biological rhythms to the length of our days. Let's begin. What is the moon? How did it come to exist? For much of the 20th century, scientists proposed three main theories about lunar origin. The fission theory suggested the moon broke away from the Earth. The capture theory suggested the moon was a separate asteroid captured by Earth's gravity. The co-accretion theory suggested the moon formed alongside Earth from the same material. Each theory had problems. None perfectly matched the evidence we collected. Today, the dominant scientific model is called the giant impact hypothesis, and it's a story almost as dramatic as mythology itself. About 4.5 billion years ago, during the early formation of our solar system, Earth was not the stable planet we know today. It was surrounded by countless planetesimals, rocky bodies of varying sizes orbiting the young sun. These bodies constantly collided, sometimes merging, sometimes ricocheting off one another. Larger bodies formed through repeated collisions. Scientists believe a Mars-sized body was in an orbit that would eventually intersect with Earth's orbit. This protoplanetary body is sometimes called Theia. It was roughly 10 to 15% the mass of Earth. This body experienced its inevitable collision with Earth approximately 4.51 billion years ago. This was no glancing blow. This was a catastrophic, head-on collision occurring at speeds of several kilometers per second. The impact was so violent, so energetically intense, that both Earth and Theia were partially vaporized. The collision generated temperatures exceeding 10,000 degrees Kelvin. Both bodies were partially melted or vaporized. The impact ejected vast quantities of material into space, creating a ring of rocky debris orbiting Earth. From this ejected material, primarily coming from the outer layers of both Theia and Earth, the Moon coalesced. Within weeks or months of the giant impact, the scattered material in orbit around Earth gradually aggregated through gravitational attraction, forming a body, our Moon. This explains several observations that previous theories struggled to account for. First, it explains why the Moon is relatively large compared to Earth. The Moon is about 1/81st the mass of Earth. This is an unusually large ratio compared to most planet-moon systems in our solar system. The giant impact hypothesis explains this. A large body collided with Earth and was partially vaporized, ejecting enough material to form a large satellite. Second, it explains the chemical composition of the Moon. The Moon's composition is remarkably similar to Earth's mantle. This suggests it formed from material that came from both Theia and Earth. Third, it explains the angular momentum of the Earth-Moon system. Before the collision, Earth would have rotated relatively slowly. The collision imparted enormous angular momentum to the system, angular momentum that is still conserved today in the orbital motion of the Moon and Earth's rotation. After the collision, Earth began a period of gradual cooling and differentiation. The Moon, meanwhile, orbited at a distance much closer than it does today. Estimates suggest it was perhaps 15,000 to 20,000 kilometers away, compared to approximately 384,400 kilometers today. As the Moon orbited this close to Earth, both bodies experienced intense tidal forces. These tidal forces had profound effects on both the Moon and Earth, effects that continue to unfold even today, billions of years later. Now, what makes Earth's Moon special? The Moon is exceptionally large relative to its primary body. The Earth-Moon system is sometimes described as a double-planet system or a binary system. The Earth and Moon orbit a common center of mass, called the barycenter, rather than the Moon simply orbiting around Earth's fixed center. This barycenter is located approximately 4,700 kilometers from Earth's center, about 1,700 kilometers below Earth's surface. This means both Earth and the Moon are orbiting this common point. While Earth's orbit around this point is much smaller than the Moon's orbit, both bodies are genuinely in orbit around their mutual center of mass. This is unusual. Most moons are so small relative to their primary planets that the barycenter is located well within the planet's interior. Earth's moon is massive enough that the barycenter is actually outside Earth's center. Second, the moon is composed primarily of rocky material, not icy material like many of the outer planet moons. This rocky composition matches predictions from the giant impact hypothesis. The moon formed from rocky material ejected during a collision between terrestrial bodies. Third, the moon has had a profound influence on Earth's evolution and the development of life. The moon's gravitational influence has shaped Earth's climate, its axis stability, its rotation rate, and its oceans. Many scientists argue that without a moon of this particular size and at this particular distance, Earth would be a very different world, possibly a lifeless world. The moon is also unique in its relationship to human culture and history. Unlike any other celestial body except the sun, the moon has been intimately connected to human mythology, culture, science, and exploration. It's the only celestial body that humans have visited. This special nature of the moon makes Earth unique among planets in the solar system. We have a moon that is large enough to produce significant tidal effects, yet not so large as to destabilize Earth's orbit or spin. We have a moon that has remained at a relatively stable distance for billions of years, allowing life to develop in a relatively consistent environment. Today, after approximately 4.5 billion years of history, the moon has acquired certain characteristics that define its relationship to Earth. The moon orbits Earth at an average distance of approximately 384,400 kilometers. This distance is not constant. The moon's orbit is slightly elliptical, not perfectly circular. At its closest approach to Earth, called perigee, the moon is approximately 356,400 kilometers away. At its farthest point, called apogee, it's approximately 406,700 kilometers away. The moon completes one orbit around Earth approximately 27.3 days. This period is called the sidereal month. However, from the perspective of someone on Earth observing the lunar phases, the cycle from full moon to full moon takes approximately 29.5 days. This longer period is called the lunar month or synodic month. Is approximately 3,474 kilometers, much smaller than Earth's 12,742 kilometer diameter. Yet, despite this size difference, the moon's gravitational influence on Earth is profound. One of the most significant characteristics of the moon is that it is tidally locked to Earth. This means the same face of the moon always points toward Earth. The moon rotates exactly once on its axis for every orbit around Earth. This isn't a coincidence, but rather the result of tidal forces and energy dissipation over billions of years. The moon's mass is approximately 7.342 times 10 to the 22nd kilograms, or about 1/81st the mass of Earth. This mass, combined with the moon's distance from Earth, creates a gravitational force that influences Earth's oceans, Earth's rotation, and Earth's long-term evolution. These current characteristics of the Moon are the result of 4.5 billion years of orbital evolution and interaction with Earth. And significantly, these characteristics are not permanent. They continue to change slowly, year after year, in response to gravitational forces between Earth and Moon. For most of human history, the Moon was imagined as dry, distant, and unreachable. Even the language we use for the dark plains on the lunar surface carries an ancient misunderstanding, because early lunar maps called them seas, maria, even though they're volcanic basalt, not water. And yet, in a quiet and surprising way, the Moon does have water. Not oceans, not rivers, not clouds, but water as a thin, scattered presence, hidden in places where sunlight almost never touches. To understand this, you have to picture the Moon's poles. Unlike Earth, the Moon has regions near the North and South Pole where the sun sits so low on the horizon that the floors of certain craters never receive direct light. These places are called permanently shadowed regions, and they are some of the coldest, most stable traps for ice in the entire inner solar system. The idea that ice could survive there isn't modern science fiction. In the early 1960s, the theoretical physicist Kenneth Watson helped popularize the idea that volatile substances like water could remain stable at the bottoms of craters that never see sunlight, even while sunlit regions would be too hot for water to persist on the surface. Then came the Apollo era. Humans walked on the Moon between 1969 and 1972, and the soil they returned seemed to show no sign of water, leading to a long period where many scientists assumed the Moon was essentially dry. But scientific instruments improve, and the Moon did not change, only our ability to see what was always there. In 2009, two spacecraft launched together, LCROS and the Lunar Reconnaissance Orbiter. LCROS deliberately impacted a crater thought to contain ice, then flew through the plume of debris while LRO observed. Those combined observations found grains of water ice in the ejected material, strengthening the evidence that ice exists in permanently shadowed regions. In 2018, analysis of data from the Moon Mineralogy Mapper instrument carried on India's Chandrayaan-1 mission revealed multiple confirmed locations of water ice in permanently shadowed regions. And in 2020, NASA reported something that reshaped the story again. Data from SOFIA confirmed water exists in sunlit areas of the Moon's surface as molecules of H2O associated with grains of lunar dust. That mattered because it suggested lunar water is not only locked away in darkness, but can also exist, at least in small amounts, where sunlight falls. By 2023, researchers created a detailed, wide-area map of water distribution using SOFIA data, and that map extended toward the moon's south pole, the region NASA intends to explore during the Artemis era. And that is where this becomes more than a scientific curiosity, because water is not just water. Water can become oxygen to breathe. It can become hydrogen and oxygen to burn as rocket fuel. It can become life support, shielding, and endurance. It can be the difference between a short visit to the moon and a sustained human presence. But the moon's water story isn't simple. A modern scientific view treats it as a cycle with sources, sinks, movements, and uncertainties. Water delivered by impacts, formed or modified by interactions with the space environment, and trapped or redistributed by temperature and terrain. A recent overview in PNAS emphasizes that while water on the moon is indicated by remote sensing and returned samples, key parameters and processes are still insufficiently constrained, and future in situ measurements are needed to substantially advance understanding. So when we say water on the moon, we should also say something else. We should say questions. How much is there really? How pure it is? How deep it sits beneath the surface? How it behaves across the lunar day and night, across seasons of sunlight and seasons of shadow. And now take a slow breath and notice the arc of this story. For centuries, humans looked up at the moon and told stories about how it moved Earth's waters. Now we are learning that the moon has water of its own, frozen in darkness, scattered in dust, waiting inside the oldest shadows. And the next era of lunar exploration is being shaped in part by the desire to understand it. Throughout human history, virtually every civilization has created myths and stories about the moon. Why? The moon's prominence in the night sky is obvious. Its dramatic changes through phases, its apparent influence on the tides and on human behavior. These made it an inevitable subject for spiritual beliefs and religious practice. In ancient Greece, the moon was personified as several different deities, depending on context and the particular aspect of the moon being represented. Selene was the Greek goddess who most directly represented the moon itself. She was depicted as a beautiful woman with a luminous face, often shown riding across the night sky in a silver chariot drawn by 2 white horses, or occasionally by white bulls. Selene was typically portrayed wearing a crescent moon as a crown or headdress, symbolizing her domain. One of the most famous myths involving Selene tells the story of her love for the mortal man Endymion. According to the myth, Selene fell in love with Endymion, a beautiful shepherd. However, as a divine being, Selene could not take a mortal as a permanent companion. He would age and die while she remained eternal. Desperate to preserve her beloved, Selene asked Zeus to grant Endymion eternal sleep. Zeus granted this request, rendering Endymion immortal, but in a state of perpetual sleep. Each night, Selene would descend from the sky to visit her sleeping lover, watching over him in the cave where he lay eternally dreaming. This myth represents the bittersweet nature of immortality and the impossibility of a permanent union between the divine and the mortal. Connected to Selene was Artemis, goddess of the hunt, identified with the moon in her crescent or half-moon phase. Artemis was a virgin goddess, one of the most famous in the Greek pantheon. Known for her association with wild animals, forests, and the hunt, she was also invoked by women during childbirth and was considered a protector of young women. In Roman mythology, the moon goddess was called Luna. The word Luna derives from Proto-Indo-European roots meaning light or brightness. Luna represented the divine embodiment of the moon in Roman religious practice and mythology. Luna was often depicted similarly to Selene, a beautiful woman in a silver chariot racing across the night sky. The Romans, like the Greeks, understood the connection between the moon and the tides, though they attributed this connection to supernatural rather than physical forces. The triadic concept of the moon goddess was particularly important in Greco-Roman religion. The moon was understood as having three aspects. Selene, or Luna, represented the goddess in heaven, the full moon at night, the luminous deity of light. Artemis, or Diana, represented the goddess on earth, the half-moon, the huntress and protector, visible in twilight. Hecate, or Hecate, represented the goddess in the underworld, the dark moon, the mysterious figure associated with magic, crossroads, and hidden knowledge. These three aspects represented different phases and different symbolism of the moon, but they were understood as facets of a single divine principle. This triadic symbolism had profound influence on later religious and philosophical traditions. In ancient Chinese mythology, the moon goddess was Chang'e, one of the most famous and beloved figures in Chinese spiritual tradition. The myth of Chang'e is one of the most poignant and complex lunar mythologies in world culture. According to the legend, in ancient times there was a skilled archer named Ho Yi. One day, the 10 suns, which normally appeared one at a time in the sky, all emerged simultaneously, creating unbearable heat and threatening to destroy all life on Earth. Ho Yi, using his extraordinary archery skills, shot down 9 of the 10 suns, saving the Earth and humanity. As a reward for his heroic deed, Ho Yi was granted an elixir of immortality by the gods. Ho Yi and his wife Chang'e lived happily together. Ho Yi carefully guarded the elixir of immortality, understanding its tremendous power. However, according to some versions of the myth, Ho Yi's apprentice discovered where the elixir was hidden and attempted to steal it. To prevent the apprentice from obtaining immortality, Chang'e made the difficult decision to drink the elixir herself. By doing this, she absorbed all of its power and prevented it from falling into the wrong hands. However, the full elixir was too powerful for a mortal to contain. hands. However, the full elixir was too powerful for a mortal to contain. As Chang'e consumed the elixir of immortality, her body began to lighten. She floated upward into the sky, rising higher and higher until she reached the moon. There, separated from Earth and her beloved husband Hao Yi, she became the moon goddess, immortal but alone. In some versions of the myth, Chang'e was transformed into a toad when she reached the moon, either as punishment for drinking the elixir without permission or as a part of the elixir's effects. In Taoist alchemy, the toad is associated with immortality and transformation. Despite her solitude and separation from those she loved, Chang'e became the goddess of the moon and a figure of profound spiritual significance in Chinese culture. She is celebrated during the Mid-Autumn Festival when families gather together to admire the full moon, share moon cakes, and tell stories of Chang'e. The Mid-Autumn Festival represents the reunion of families and the blessing of the full moon. Chang'e's myth is quite different from the Greek Selene myth. While Selene maintains connection to her beloved through nightly visitations, Chang'e is forever separated from Hao Yi. While Selene is depicted as eternally beautiful and radiant, Chang'e is sometimes depicted as a toad, less beautiful by conventional standards, yet somehow more profound in her sacrifice and transformation. Chang'e represents themes of self-sacrifice, duty, transformation, and the bittersweet nature of immortality. Beyond the Greek and Chinese traditions, the moon held profound significance across virtually all human cultures. In Hindu mythology, the moon is personified as Chandra, typically depicted as a male deity who rides across the sky in a chariot drawn by white horses or antelope. Chandra is associated with the mind, with coolness, with calmness. In Hindu cosmology, Chandra, the moon, and Surya, the sun, are cosmic forces in eternal balance. In Mesopotamian mythology, the moon was Sin, or Nana, one of the most important deities in the Sumerian, Akkadian, and Babylonian pantheons. Sin was often depicted as a bearded man with a crescent moon in his headdress. He was the father of the sun god Shamash and was venerated as a god of wisdom and the measurement of time. In Egyptian mythology, the moon was associated with several deities depending on the period and context. Thoth, god of wisdom and writing, was sometimes depicted with the lunar disk. Khonsu, the falcon-headed god, was another lunar deity associated with time, healing, and fertility. In Mesoamerican mythology, particularly among the Aztecs, the moon held special significance. When the gods created the world, two deities sacrificed themselves to become the sun and moon. Tecusistecatl, the moon god, hesitated before making his sacrifice. As punishment, the gods struck him with a rabbit, which is why some people claim to see the outline of a rabbit on the moon's surface. In Japanese mythology, Tsukuyomi is the moon god, or sometimes goddess, born from the purification rituals of the creator Izanagi. Interestingly, in Japanese mythology, the sun and moon are siblings but separate, unlike the Greek system where Artemis and Helios are siblings. In Australian Aboriginal mythology, the Yolngu people of northeastern Arnhem Land identified a direct link between the moon and the tides. They attributed this link mythically to the moon filling with water and emptying again. This is a remarkably sophisticated understanding of lunar influence on ocean water, one that many cultures eventually arrived at through observation. What's remarkable across all these mythologies is a consistent pattern. The moon is personified, treated as a conscious being with agency and emotional complexity. The moon is understood as affecting human life, determining festivals, marking time, influencing tides, affecting behavior and emotion. Most cultures, regardless of geography or historical connection, arrived at the understanding that the moon influences the tides. The mechanism might be explained through mythology, the moon filling and emptying, or through gods directing the waters, but the observation itself was nearly universal. This near universal attention to the moon reflects something profound about human nature. We look up at the night sky, we see the moon, we notice patterns, its phases, its position, its apparent influence on the world. We create stories to explain these observations. These stories become part of our culture, our religion, our understanding of the cosmos, and our place within it. We've now explored the moon and lunar mythology in depth. So what is Apollo's connection to this story? Why does a sun god deserve significant discussion in a documentary primarily about the moon? The answer lies in understanding both ancient mythology and modern space exploration. Apollo represents the bridge between mythology and science, between the ancient human attempt to understand the cosmos and the modern scientific method. In Greek mythology, Apollo is one of the most important and complex Olympian deities. He is the son of Zeus and the Titaness Leto, and he is the twin brother of Artemis, goddess of the hunt, and, by association, goddess of the moon. Apollo is principally known as the god of the sun, though this association requires nuance. In early Greek mythology, the actual personification of the sun was Helios, a distinct deity who drove a golden chariot across the sky each day, bringing light to the world. Over time, particularly during the Hellenistic period, the cult of Apollo absorbed many of Helios's characteristics and roles. Apollo became associated with the sun, with light, with brilliance. Apollo is typically depicted with glowing golden hair, embodying solar radiance. However, Apollo's portfolio extended far beyond simply being the sun god. He was the god of music, poetry, and the arts. He played the lyre, an instrument he invented according to mythology. He was the leader of the Muses, the 9 goddesses of artistic and intellectual endeavors. Apollo was also the god of healing and medicine. He was the god of prophecy, the patron deity of the oracle at Delphi, one of the most important religious sites in ancient Greece. Suppliants would travel from across the known world to consult the Pythia, the priestess of Apollo at Delphi, seeking prophecy and guidance. Additionally, Apollo was the god of colonization, providing oracular guidance to those founding new colonies. He was the god of archery, of protection of herds and flocks, and of plague. He could both inflict disease and cure it. The sibling relationship between Apollo and Artemis is particularly significant. Apollo, the god of the sun and light, was the twin brother of Artemis, goddess of the moon and darkness. This celestial partnership reflects the fundamental astronomical reality that these two bodies dominate our sky and alternate throughout the day and night cycle. In artistic representations, Apollo and Artemis are often depicted together, or their attributes are symbolically linked. This represents the ancient understanding that these two celestial bodies are intimately connected, that day and night, sun and moon, light and darkness are complementary pairs rather than opposites. Apollo's connection to the moon is subtle but important. While Artemis directly embodies the moon, Apollo's role as the sun god makes him the counterpart and complement to lunar deities. Apollo represents the bright day. Artemis and the moon represent the mysterious night. Significantly, NASA named its lunar exploration program Apollo. The Apollo program, which resulted in the first human landing on the moon in 1969. This naming choice represents a deliberate connection between ancient mythology and modern space exploration. Later, NASA created the Artemis program, named after Apollo's twin sister, to return humans to the moon and eventually to establish a sustained human presence there. This modern naming convention explicitly references the mythological partnership between Apollo and Artemis, the sun and the moon. This naming reflects a profound truth. The moon cannot be understood in isolation. The moon's relationship to Earth is part of a larger cosmic system that includes the sun. The tides on Earth are created not just by the moon, but by the combined gravitational influence of both the moon and the sun. The moon's position relative to the sun determines the phases we observe. The cycles that the moon creates are intimately linked to solar cycles. Apollo, then, represents not simply a sun god, but the principle of the sun as it relates to understanding the moon. Apollo is the complementary force to lunar deities. Apollo is the light that makes the moon visible and distinguishes its features. Apollo is the force that, combined with the moon, creates the tides. Now we turn to the core scientific content of this episode. We'll spend the majority of our remaining time exploring the physics behind the tides, one of nature's most profound demonstrations of how gravity works across vast distances. Let's begin with the most fundamental principle: gravity. Every object in the universe with mass exerts a gravitational force on every other object. The strength of this force depends on two factors: the mass of each object and the distance between them. This relationship is described by Newton's law of universal gravitation, formulated by Isaac Newton in 1687. The gravitational force between two objects is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. In mathematical form, the force equals the gravitational constant times the first mass times the second mass divided by the distance squared. The inverse square law is crucial to understanding tides. If you double the distance between two objects, the gravitational force decreases to 1/4. If you triple the distance, the force decreases to 1/9. Now here's the critical insight that leads directly to tides. While Earth as a whole is attracted to the moon, different parts of Earth are at different distances from the moon. The side of Earth facing the moon is closer to the moon than Earth's center is. Therefore, the side of Earth facing the moon experiences a stronger gravitational pull from the moon than Earth's center does. Conversely, the far side of Earth, the side facing away from the moon, is farther from the moon. Therefore, the far side experiences a weaker gravitational pull from the moon than Earth's center does. This difference in gravitational force across Earth's diameter creates what's called the tidal force. It's not the absolute strength of the moon's gravity that creates tides, but rather the differential, the difference between the moon's gravitational pull on different parts of Earth. To visualize this, imagine Earth as a sphere with 3 regions: the near side facing the moon, Earth's center, and the far side opposite the moon. The moon pulls hardest on the near side. It pulls less hard on the center. It pulls even less hard on the far side. This differential pull creates a stress in Earth, a stretching effect. The entire planet is being stretched slightly along the Earth-Moon line, like taffy being pulled at both ends. For a solid planet composed of rock, this stretching is relatively small, but for the liquid oceans covering Earth's surface, this stretching has dramatic effects. The moon's differential gravitational pull doesn't simply stretch Earth evenly. Instead, it causes something remarkable. The oceans actually bulge toward the moon. Here's why. The moon's tidal force on the near side of Earth pulls the ocean water on that side directly toward the moon. On the side of Earth closest to the moon, vast amounts of water accumulate, creating a bulge. a region where sea level is elevated above average by typically 1 to 2. But here's where it gets interesting. There's also a bulge on the far side of Earth, on the side facing away from the moon. This seems counterintuitive. If the moon is pulling water toward itself on the near side, why would water also bulge outward on the far side? The answer involves understanding how gravity works across a sphere. On the far side of Earth, the moon's gravitational pull is weaker. Earth's center experiences a stronger pull than the far side does. This creates a differential effect. Earth's center is pulled more strongly toward the moon than the far side is. From the perspective of someone on the far side of Earth, this is equivalent to saying they're being pushed away. If Earth's center is accelerating toward the moon faster than the far side is, then the far side experiences a net acceleration away from the moon. This creates a centrifugal effect on the far side. Water bulges outward away from Earth's center and away from the moon. So we get two bulges, one on the side of Earth facing the moon, pulled by the moon's gravity, one on the side of Earth facing away from the moon, pushed outward as Earth's center is pulled harder than the far side. These bulges are called tidal bulges. They're not stationary features. Rather, they're created by the distribution of water responding to differential gravitational forces. Now here's what's crucial. Earth is rotating. As Earth rotates, the bulges created by the moon's tidal force stay oriented toward the moon. This means that as Earth rotates beneath these bulges, different parts of Earth's surface pass through regions of high tide, where a bulge is, and low tide, where water has moved away. In a 24-hour period, as Earth rotates once, any given location on Earth passes through two bulges and two non-bulge regions. This means that most coastal areas experience two high tides and two low tides per day. This is crucial. Tides don't occur because the moon orbits overhead. Tides occur because the moon exerts a differential gravitational force on Earth, creating bulges in the ocean. As Earth rotates, these bulges sweep across the surface. The timing of high tides also reflects the moon's position. In a 24-hour period, Earth rotates once, but the moon orbits Earth approximately every 27.3 days. This means that relative to the stars, the moon appears to move backwards slightly each day, about 50 minutes per day. This is why high tides occur about 50 minutes later each day than they did the previous day. While the moon is the primary driver of tides, the sun also contributes. The sun is much more massive than the moon, about 330,000 times more massive. However, the sun is also much farther away from Earth than the moon is, about 400 times farther. Applying the inverse square law, the sun's gravitational influence on tides is about 400 squared times weaker in distance, but 330,000 times stronger in mass. Working through the mathematics, the sun's tidal effect is roughly 46% that of the moon's tidal effect. In other words, the sun's tidal contribution is about half that of the moon's. The sun, like the moon, creates its own tidal bulges. The sun pulls on Earth's near side more strongly than on the far side, creating differential gravitational effects that generate tidal bulges similar to those created by the moon. The interplay between lunar tides and solar tides creates fascinating phenomena called spring tides and neap tides. Spring tides occur when the sun and moon align on the same side of Earth at new moon or on opposite sides of Earth at full moon. In either case, the tidal bulges created by the sun and moon reinforce each other. The combined effect creates maximum tidal range, the highest high tides and the lowest low tides. Neap tides occur when the sun and moon are at right angles to each other at first quarter and third quarter moons. In these configurations, the solar tidal bulges are perpendicular to the lunar tidal bulges. The solar tides partially cancel out the lunar tides, resulting in the minimum tidal range, the lowest high tides, and the highest low tides. This monthly cycle of tidal range from spring to neap and back to spring occurs with the lunar month, approximately 29.5 days. This is observable and predictable, and has been used by sailors and coastal peoples for thousands of years, though they may not have understood the underlying gravitational mechanism. What's remarkable is that ancient peoples noticed these patterns. They tracked the correlation between lunar phases and tidal ranges. They developed empirical knowledge that allowed them to predict tides with reasonable accuracy, even without understanding gravity. This represents a profound observation. Without scientific instruments, without advanced mathematics, ancient peoples recognized a consistent relationship between the moon's appearance and the behavior of the oceans. This observation was so reliable that it became incorporated into maritime knowledge and oral traditions. The mythology of the moon in this light can be understood as ancient humanity's attempt to explain these observations. The stories of lunar deities controlling the waters, the myths connecting the moon's movements to oceanic changes. These weren't wrong, they were proto-scientific explanations, attempts to understand cause and effect using the conceptual tools available. Now we come to one of the most profound and least understood aspects of the Earth-Moon system. The moon is slowly moving away from Earth, and this recession is linked directly to tidal dissipation. Here's the mechanism. The tidal bulges created by the moon don't align perfectly with the Earth-Moon line. Because Earth is rotating faster than the moon orbits, the bulge is actually displaced ahead of the Earth-Moon line, pushed slightly ahead by Earth's rotation. This offset creates a subtle but significant effect. The displaced bulge exerts a gravitational pull on the moon that's not perfectly radial, pointing from Earth's center to the moon. Instead, the pull has a slight component that accelerates the moon in its orbit. This acceleration causes the moon to gain orbital energy. As the moon gains energy, its orbit expands. The moon spirals outward, away from Earth. Simultaneously, the gravitational interaction between the displaced bulge and the moon creates a torque that affects Earth's rotation. This torque acts to slow down Earth's rotational speed. This energy transfer from Earth's rotational energy to the moon's orbital energy is dissipated through friction in the oceans and the Earth's crust as tides are created. Energy that was in Earth's rotation is converted into heat through tidal friction. The rate of this process is measurable. The moon is currently receding from Earth at approximately 3.8 centimeters per year. This means that in the distant past, the moon was much closer to Earth than it is today. Calculating backward using this recession rate, about 1.2 billion years ago, the moon was close enough that lunar tides would have been approximately 6 times more powerful than they are today. The tidal effects during this period would have been astronomical, causing massive movements of water and extremely rapid tidal currents. Going even farther back, shortly after the moon's formation, 4.5 billion years ago, it was much closer to Earth. Early tidal interactions would have been so violent that they would have heated both Earth and the moon significantly. More extreme models suggest that at certain points in Earth's early history, the moon might have been close enough that its tidal influence would have literally torn apart planetary bodies if they had been as rigid as modern planets. The tidal forces would have been extreme. This recession of the moon has profound implications for Earth's future. Currently, the moon is receding. Eventually, though, it won't recede forever. The interaction between Earth and Moon will eventually reach an equilibrium state where the Earth-Moon system is more tightly bound. In the very distant future, we're talking about timescales of trillions of years. The complex dynamics of the Earth-Moon system, combined with the Sun's eventual evolution, might lead to scenarios where the Moon is either captured back into a closer orbit or is ejected from Earth's orbit altogether. But that's a story for hundreds of billions of years in the future. What's significant is that the moon we observe today is different from the moon of the past. It was closer. The tides were more dramatic. The effects on Earth were more pronounced. This reminds us that even celestial bodies are not permanent or unchanging. The moon is part of a dynamic system. It's moving, changing, evolving. The tide you watch at a shoreline feels like a daily rhythm, a gentle rise, a gentle fall, something that returns reliably, like breathing. But tides are not only a shoreline event, they are a planetary force. NASA describes tides as a result of the gravitational pull between Earth and Moon, which slightly distorts the shapes of both worlds. This is the part most people never feel. The ocean moves, so we notice it, but the solid Earth is also distorted subtly in response to the moon's pull. It's not something you see with your eyes, but instruments can detect it, and the ocean's movement is the visible expression of the same gravitational story. Now, let's widen the time scale. Over geological time, tides do something that is almost poetic in its inevitability. They take motion and turn it into heat. They take spinning and trade it slowly for orbital change. They convert the dance between Earth and Moon into a long, quiet evolution of the system. You can think of it like this. The moon's gravity does not lift the ocean straight upward like a hand under a bowl. It shifts and squeezes water around the globe because water slides more easily across Earth's surface than it rises. So bulges form, one on the side facing the moon and one on the side opposite. As Earth rotates through them, coastlines pass through high tide and low tide, most often twice each day. But tides do not line up perfectly with the moon's position. There is an extra timing offset because the moon orbits in the same direction Earth rotates, and because the tidal bulges are not perfectly aligned with the moon. NASA notes that this extra time is about 50 minutes, which is why tide timing drifts day to day. Now bring the sun into the picture. NASA explains that the sun is far more massive than the moon, but much farther away, so its tide-generating force is a little less than half of the moon's. When sun, moon, and Earth line up, we get spring tides with especially high highs and low lows. When sun and moon are at right angles, we get neap tides, more moderate and restrained. All of this is the everyday tide story. The deep time tide story begins when you realize the Earth is not perfectly smooth. Continents interrupt the flow. Ocean basins shape resonance. Storms, winds, and coastlines bend the tide into local patterns. And in the long view, these details matter because they control how efficiently tidal energy is dissipated. That means the changing shape of Earth, continents assembling and breaking apart, ocean gateways opening and closing, can change how tides behave across hundreds of millions of years. So tides are not only an effect of the moon, they are also a feedback loop between Earth's geography and the Earth-Moon system's long-term evolution. And there is another detail, subtle but profound. Earth's gravity deforms the moon too, and NASA notes that these lunar tides are measurable with lasers. In some cases, they leave visible marks like young cliffs called lobate scarps, shaped by the moon's contraction and by tidal stresses. So the tidal relationship is not one way. Earth shapes the moon shapes Earth, and both bodies slowly record that interaction in their surfaces, their motions, and their histories. This is why tides belong in an episode about Apollo and Artemis. Because when we travel to the moon, we are not traveling to a dead rock. We are traveling to a partner in a gravitational relationship that has been shaping Earth for billions of years. If you want a quiet kind of wonder, hold on to this thought. Every tide you've ever seen is connected to the deep history of the Earth-Moon system. Every shoreline carries the signature of a relationship written in gravity. And every mission that returns to the moon returns, in a sense, to the source of one of Earth's most ancient rhythms. One of the most remarkable features of the moon is that the same side always faces Earth. We never see the far side of the moon from Earth's surface. This phenomenon is called tidal locking, or synchronous rotation. The moon is tidally locked to Earth. This means the moon rotates on its axis exactly once for every orbit it completes around Earth. The rotation period equals the orbital period, approximately 27.3 days. Why did this happen? The answer involves tidal forces and energy dissipation. When the moon was young and closer to Earth, tidal forces from Earth deformed the moon, creating bulges in the moon's solid rock, just as the moon creates bulges in Earth's oceans. As the moon rotated, these bulges were stretched and shifted by the deformational stresses, creating internal friction and energy dissipation. This energy dissipation in the moon's interior caused it to gradually slow down. The moon's rotation decelerated over time. Eventually, the moon's rotation matched the rate at which it orbited Earth. Once the moon's rotation matched its orbital period, once tidal locking occurred, the tidal bulges were no longer shifted relative to the Earth-Moon line. The bulges could remain stationary relative to Earth. With no shifting, there was no continuing friction and energy dissipation. At this point, the system reached equilibrium. The moon's rotation stopped changing. It became tidally locked. This is a common phenomenon in the solar system. Most of the moons of the planets are tidally locked to their primary planets. Mercury, the closest planet to the Sun, is tidally locked to the Sun. The same side always faces the Sun. Some researchers have speculated that Earth itself might eventually become tidally locked to the Sun in the extremely distant future, if the Sun's tidal forces eventually override the Moon's influence. But this is a scenario many billions of years in the future. The tidal locking of the Moon has had profound effects on human history. Because the same side always faces Earth, early humans could only observe one face of the Moon. The far side of the Moon, invisible from Earth, became mysterious and legendary. Only when human space exploration allowed us to send spacecraft around the Moon in the 1960s did we finally see the far side directly. The Moon's tidal locking also means that the Moon rotates very slowly from the perspective of someone on its surface. A lunar day, the time it takes for one lunar location to rotate from facing Earth to facing away and back, is approximately 29.5 days. This slow rotation means that the lunar day-night cycle is extreme. Locations on the moon experience about 2 weeks of continuous sunlight, followed by about 2 weeks of continuous darkness. This creates extreme temperature variations from nearly 130 degrees Celsius in direct sunlight to nearly negative 180 degrees Celsius in darkness. Life as we know it could not survive in such extreme conditions. Yet the moon's tidal locking tells us something profound. It tells us that the tidal forces between celestial bodies can literally reshape them, can slow their rotation, can lock them into synchronous motion with their primary bodies. The tidal interaction between Earth and Moon doesn't just affect the Moon, it also profoundly affects Earth. As the Moon's tidal bulge on Earth is displaced ahead of the Earth-Moon line by Earth's rotation, there's a subtle gravitational interaction that has been accelerating the Moon. We discussed this earlier. But there's a reaction to this. For every action, there's an equal and opposite reaction. The same interaction that accelerates the Moon also exerts a torque on Earth that opposes Earth's rotation. This torque acts to slow down Earth's rotational speed. Over time, this means Earth rotates more slowly. The effect is measurable. About 1 billion years ago, a day on Earth was approximately 19 hours long. Today, a day is 24 hours. Going back further to the early days of Earth's history, days were even shorter. The current rate of slowing is about 1.7 milliseconds per century. This means that in the next century, days will be approximately 1.7 milliseconds longer than they are today. This slowing has profound implications. Life on Earth evolved within the context of a specific day-night cycle and a specific rotational speed. Changes to Earth's rotation rate would have affected circadian rhythms, ocean currents, weather patterns, and many other aspects of Earth's environment. The tidal interaction between Earth and Moon has essentially been gradually reducing Earth's rotational energy and converting it to orbital energy for the Moon. Eventually, if this process continued long enough, and we're talking about timescales of trillions of years, long after the sun has become a red giant and possibly engulfed Earth, Earth's rotation might slow to match the Moon's orbital period. Earth might become tidally locked to the Moon, with the same side always facing the Moon. However, this is almost certainly not going to happen because the sun's evolution will dramatically alter the Earth-Moon system long before such a state is reached. The fact that Earth is slowly rotating more slowly is a demonstration of how intimately connected all parts of a planetary system are. A change in how the Moon orbits affects Earth's rotation. A change in Earth's rotation affects the Moon's orbit. The system is in constant, dynamic exchange. The tides don't just affect Earth's oceans and rocks, they also affect the biological systems that inhabit Earth. Many organisms have evolved intricate biological rhythms that are synchronized with tidal cycles. This is particularly true for organisms in coastal environments where tidal changes are most dramatic. Shore-dwelling creatures, crustaceans, mollusks, certain fish species often have behavioral patterns synchronized to the tidal cycle. They emerge from their burrows or hiding places at specific tidal phases. At a cellular level, researchers have discovered that many organisms possess circatidal clocks, biological timing mechanisms that follow a tidal cycle of approximately 12.4 hours, the tidal cycle period. These circatidal clocks are distinct from circadian clocks, which are daily rhythms, and are found in organisms ranging from marine worms to some fish species. The mechanism of how these circatidal clocks work is still not completely understood. Unlike circadian clocks, which appear to have well-established genetic and neurological basis in most organisms, circatidal clocks remain somewhat mysterious. It's hypothesized that circatidal clocks are entrained by changes in physical factors, changes in pressure from tidal currents, changes in sediment movement, changes in salinity, rather than by light, which is the primary entrainment for circadian clocks. Humans also show subtle tidal influences. Some research suggests that human circatidal clocks exist at a cellular or tissue level, though we're not consciously aware of them. There have been claims throughout history that the moon affects human behavior. The word lunacy derives from luna, Latin for moon, reflecting the historical belief that the moon caused insanity. However, scientific evidence for a direct effect of the moon on human behavior or mental health is limited. What is scientifically established is that the moon affects Earth's light environment, particularly the brightness of the night sky during full moon phases, and that this affects circadian rhythms and sleep patterns in some individuals. The tidal effects on biology represent an ancient dance. Organisms have had over 1 billion years to evolve in response to tidal cycles, and many species show remarkable synchronization with these cycles. This tells us something profound. Life on Earth has not evolved in isolation from astronomical phenomena. Rather, life has evolved in intimate interaction with those phenomena. The rhythms of the cosmos are literally written into the biology of organisms, into their genes, into their cellular machinery, into their behavior. Let's dive deeper into the physics of tidal dissipation, one of the most important and least understood aspects of planetary science. Tidal dissipation is the process by which tidal energy is converted into heat through friction. In Earth's case, this friction occurs in several locations. In the oceans, as tidal currents flow across the sea floor and through shallow passages, friction converts kinetic energy of the water into heat. In the Earth's crust and mantle, tidal deformation, the flexing of rock in response to tidal stresses, causes friction and energy dissipation. The rate of tidal dissipation in Earth is not constant over geological time. It depends on ocean basin geometry, seafloor topography, and many other factors that change as continents drift and ocean basins evolve. The tidal dissipation rate also affects the long-term evolution of the Earth-Moon system. More dissipation means more rapid changes in Earth's rotation rate and the Moon's orbit. During certain periods of Earth's history, when ocean basins had different configurations, tidal dissipation may have been significantly higher than it is today. This would have meant more rapid changes to Earth's rotation rate and the Moon's orbit. For example, when all continents were joined into a supercontinent called Pangaea, ocean basin geometry was very different, and tidal dissipation may have been notably different. Changes in tidal dissipation affect not just the Moon's orbit, but also Earth's climate and biology. Changes in tidal range affect ocean circulation patterns. Changes in day length affect the distribution of solar energy across Earth's surface. Some researchers hypothesize that variations in tidal dissipation might have contributed to certain climate cycles and mass extinction events, though this remains a topic of active research. The evolution of the Earth-Moon system is thus tightly coupled to the geological evolution of Earth itself. As Earth changes, as continents drift, as ocean basins evolve, as the structure of the planet transforms, the Moon's orbit and Earth's rotation continue to evolve in response. This is a profound realization. The Moon is not simply affecting Earth. Rather, Earth and Moon are in constant, dynamic interaction. They shape each other. They evolve together. Today, we can predict tides with remarkable accuracy thanks to sophisticated scientific methods and technology. Satellite technology, particularly systems like TOPEX and Poseidon, and more recent satellite altimetry missions, allows us to measure sea surface heights with centimeter-level precision. These measurements reveal tidal patterns across the entire globe. Sophisticated computer models of Earth's oceans and the gravitational interactions of the Earth-Moon-Sun system allow scientists to predict tidal heights and times far in advance. Laser ranging to retroreflectors left on the Moon by Apollo astronauts allows us to measure the Moon's distance to the centimeter level and to directly observe its recession. These observations confirm that the Moon is indeed receding at approximately 3.8 centimeters per year, validating the theoretical predictions of tidal evolution. Seismic networks also provide information about how tides affect Earth's interior. The constant flexing of Earth's crust and mantle from tidal forces creates seismic signals that can be detected and analyzed. This combination of observational data and theoretical modeling has created our modern understanding of tidal mechanics, an understanding that would have seemed miraculous to ancient peoples who could only observe the tides without understanding their cause. Despite our sophisticated understanding of tides, mysteries and anomalies remain. While the giant impact hypothesis is the dominant scientific model for lunar origin, some details remain puzzling. The chemical composition of the moon is remarkably similar to Earth's mantle, which fits the hypothesis well. However, some isotopic ratios in lunar rocks are slightly different from those in Earth rocks in ways that are not fully explained. Recent research has suggested that the impactor, Theia, may have had a composition different from Earth, but the exact nature of Theia's composition and origin remains somewhat mysterious. Tidal heating of moons has become an important topic in astrobiology. Jupiter's moon Io is incredibly volcanically active, possibly more so than Earth, due primarily to tidal heating from Jupiter's gravity. Europa, another Galilean moon, may have liquid oceans beneath its icy crust, potentially kept warm by tidal heating. Yet the exact mechanisms of how tidal friction generates heat and how that heat is distributed through a moon's interior are not completely understood. While we can predict average tidal patterns well, local variations in tidal heights and times are more difficult to predict. These variations depend on the specific geometry of ocean basins, the presence of islands, the depth of the seafloor, and many other local factors. Some coastal regions have unusual tidal patterns, places where tidal predictions are historically inaccurate despite our sophisticated models. The Bay of Fundy in Canada is famous for having the largest tidal range in the world, over 16 meters in some locations. This is due to specific geometric properties of the bay that create resonances between the natural frequency of tidal oscillations and the shape of the bay. But not all unusual tidal regions are completely understood. While we understand that the tidal bulge is offset from the Earth-Moon line due to Earth's rotation, the exact degree of this offset and how it varies over time are not completely characterized. This lag directly affects the rate at which the moon recedes and Earth's rotation slows. Small changes in the lag can lead to significant differences in long-term evolutionary predictions. Research into ancient tidal patterns using geological evidence from rocks that record tidal cycles from Earth's past has revealed that tidal patterns in Earth's past were sometimes quite different from today. Some ancient periods appear to have had unusual tidal resonances that created larger than expected tidal ranges or unusual tidal patterns. The mechanisms creating these ancient anomalies are not completely understood. Most popular explanations of tides focus on the simple two-bulge model, one bulge facing the moon and one on the opposite side. However, tides are actually three-dimensional phenomena with more complex patterns. Recent satellite observations have revealed that there are subtle higher-degree tidal modes, tidal patterns with 3, 4, 5, or more bulges that are normally small but measurable. Understanding these higher-degree modes and their effects on ocean dynamics remains an active area of research. As we consider the mysteries of current tidal science, we must also ask, what is the future of the Earth-Moon system? If the current process of tidal dissipation continues indefinitely, Earth might eventually become tidally locked to the moon. In this scenario, the same side of Earth would always face the moon. This would take an extraordinarily long time, potentially over 1 trillion years. A tidally locked Earth would experience extreme environmental changes. The side always facing the moon would have permanent tidal effects. The side always facing away would experience permanent tidal effects of a different character. The day-night cycle as we know it would cease to exist. Life, as it evolved on Earth with the current day-night cycle, would presumably be unable to survive such changes. The moon is receding from Earth. Eventually, this recession reaches a maximum distance, at which point the dynamics might shift. But that maximum is still millions of years away. However, before the moon recedes as far as it might naturally go, the evolution of the sun will intervene. In about 5 billion years, the sun will exhaust its core hydrogen and begin to fuse hydrogen in a shell around the helium core. The sun will expand dramatically, becoming a red giant. The sun's diameter may expand to encompass Mercury's orbit and possibly Venus's orbit. If the sun expands enough to engulf the moon will be drawn into the sun and destroyed. If the sun expands enough to significantly alter the Earth-Moon distance or the gravitational dynamics between them, the entire Earth-Moon system may be disrupted. In some models, the sun's expansion might actually accelerate the moon's recession, pushing it farther away from Earth. Even without waiting for the sun's evolution, the Earth-Moon system will continue to change. The moon's recession continues at about 3.8 centimeters per year. Over human timescales, this is imperceptible, but over geological timescales, it's significant. As the moon recedes, the tidal range will gradually decrease. The tides in the distant future will be less dramatic than they are today. This has implications for life. The tides are crucial for many ecosystems, particularly coastal and estuarine ecosystems. Changing tidal ranges could affect these ecosystems. Interestingly, humans are planning to return to the moon and establish permanent bases there. Understanding the current moon and its properties will be crucial for this endeavor. The moon, as it exists today, is a relatively stable platform for human exploration and colonization. But recognizing that the moon is slowly receding from Earth, that it's part of a dynamic system that's constantly evolving, reminds us that even celestial bodies are not permanent or unchanging. Apollo was the name NASA chose for the first era of human lunar landings, and now the return is named Artemis. In mythology, Artemis and Apollo are twins, moon and sun, two lights that define the rhythm of day and night. In human history, Apollo was a short, brilliant era. Footprints, samples, a handful of missions, then silence. Artemis is different by design. Artemis is not only a return to the surface, it is a return with a plan for sustained access, new technologies, and a new target region that Apollo never explored, the lunar South Pole. NASA's Artemis 3 page explains that Artemis 3 is currently planned for 2027 and will mark humanity's first return to the lunar surface in more than 50 years, with astronauts exploring the region near the lunar South Pole. The South Pole is challenging: extreme lighting, long shadows, rugged terrain, but it also holds scientific promise, including permanently shadowed regions that can preserve ice. The mission architecture is also a major shift. NASA describes Orion as the crew's ride to and from Earth and into and out of lunar orbit. NASA also states that it selected SpaceX to provide the human landing system that will transport Artemis 3 astronauts from Orion in lunar orbit down to the lunar surface and back. That lander concept is based on Starship, including an uncrewed demonstration landing mission before a crewed landing, once requirements and safety standards are met. NASA describes Artemis 3 using a near rectilinear halo orbit, chosen for long-term Artemis goals like near constant communications with Earth and access to sites across the Moon, and also as the planned orbit for assembling the Gateway Lunar Space Station in future missions. This means that Artemis is not only about one landing, but about building a system, a repeatable route between Earth, lunar orbit, and the surface. On the surface, NASA says the crew will conduct a series of moonwalks, collecting images and video, surveying geology, retrieving samples, and gathering data to meet specific scientific objectives. NASA also notes that the view at the South Pole will look very different from Apollo's equatorial photographs, with the sun hovering low, casting long shadows that crews will explore with headlamps and navigational tools. NASA states that Axiom Space will provide the Artemis 3 surface suits and spacewalk systems. And now, connect this back to what we discussed earlier: water. NASA's overview of lunar water describes strong evidence for ice in permanently shadowed regions, and also describes confirmed water in sunlit areas, plus ongoing mapping and research that ties directly to the South Pole region targeted for Artemis-era exploration. A sustained presence on the Moon becomes more plausible if local resources, especially water, can be characterized and potentially used. This is why the Artemis story belongs in the same breath as tides, and in the same calm frame as mythology. The Moon is not just an object. It is a force that shapes Earth's oceans, and it is a destination that now shapes human plans, human engineering, and human imagination again. Apollo proved we could reach the Moon. Artemis is asking a deeper question. Can we learn how to return reliably and work there long enough to understand it, to study its ice, its geology, and its history, and to bring that knowledge back home? And if you listen closely, even the names tell the story. Apollo, Artemis, sun and moon, two halves of one ancient pattern, now expressed not in myth alone, but in missions, trajectories, and the slow unfolding of a new lunar era. We have spoken of gravity. We have spoken of orbital mechanics and the slow, grinding recession of the moon over billions of years. But there is a softer, more intimate side to this story. A story written not in stone or equation, but in the code of life itself. For 4 billion years, the moon has been more than a rock in the sky. It has been a metronome, a cosmic clock ticking above the developing biosphere of Earth. While the sun dictates the rhythm of the day, the circadian rhythm of awake and asleep, the moon dictates a longer, deeper rhythm, the circulunar cycle. And for millions of species, this rhythm is not a subtle influence. It is a matter of life and death. Consider the intertidal zone, that narrow strip of the planet that exists between the high tide mark and the low tide mark. This is a chaotic, harsh environment. Twice a day, it is drowned in salt water. Twice a day, it is exposed to the baking sun and drying air. To survive here, life had to adapt to the rhythm of the moon. Creatures like barnacles, mussels, and crabs learned to seal their shells when the tide receded and open them when the moon pulled the waters back. This rhythm is so deeply ingrained that if you take an oyster from the ocean and move it 1,000 miles inland inside a dark laboratory, it will eventually adjust its opening and closing to match the position of the moon over the laboratory. It still feels the tide even where there is no water. Many evolutionary biologists believe that these tidal pools, these distinct rhythm-driven environments created by the moon, were the laboratories where life learned to leave the ocean. The moon forced marine life to endure periods of air exposure, pushing evolution toward lungs, toward limbs, toward the ability to walk on land. In a very real sense, we may owe our existence as land-dwelling creatures to the tides. But the moon's influence goes deeper than just the movement of water. It is also about light. In the open ocean, the Great Barrier Reef offers one of the most spectacular displays of lunar synchronization on Earth. For most of the year, the coral looks like stone. But once a year, usually a few nights after the full moon in late spring or early summer, the entire reef explodes into life. Billions of coral polyps release their eggs and sperm into the water simultaneously. It is a blizzard of biological material visible from space. But how do they coordinate this? They have no eyes. They have no calendars. They have the moon. The corals sense the specific intensity of moonlight. They sense the slight increase in water temperature, and potentially they sense the subtle shift in gravity itself. They wait for the full moon to pass, and then, in a synchronized global dance, they spawn. If they were out of sync by even a few hours, their reproductive material would be diluted and lost. The moon provides the signal that ensures their survival. We see this pattern repeated everywhere. On the beaches of California, the grunion fish ride the highest high tides, the spring tides, to strand themselves on the sand. They lay their eggs at the very top of the beach, where the water will not reach them for 2 weeks. The eggs incubate in the warm sand, safe from aquatic predators. Exactly 2 weeks later, when the next spring tide rises to that same height, the waves wash over the eggs, triggering them to hatch instantly, and the baby fish are swept back into the ocean. They are born on a schedule dictated entirely by the orbital mechanics of the Earth-Moon system. Sea turtles hatch under the cover of night, using the reflection of the moon on the water to guide them to the sea. Insects use the polarization of moonlight to navigate across vast distances. And what of us? Human beings have largely insulated ourselves from the natural world with electric lights and climate control. We often forget that we too evolved under the light of the moon. For thousands of years before streetlights, the full moon was the only time humans could effectively hunt, travel, or gather at night. Our social structures, our storytelling, our very perception of time was lunar. The word month comes from the word moon. Our calendars were originally moon charts. There is a persistent debate in science about how much the moon still influences human biology. Some studies suggest subtle links between lunar cycles and sleep quality, with people sleeping slightly less deeply during the full moon, even in windowless sleep labs. It is a faint echo, perhaps, a remnant of a time when the full moon meant danger from predators or opportunity for activity. But whether the biological link is strong or weak in modern humans, the psychological link remains unbreakable. We are drawn to the moon. When it is full and rising low over the horizon, massive due to the moon illusion, we stop and stare. We feel a sense of awe that is distinct from the way we feel about the sun or the stars. The sun is blinding power. It is the source of energy. But the moon is a companion. It is a mirror reflecting the sun's light into the darkness. It is the nightlight of the species. So when we look at the moon, we are not just looking at a rock that causes tides. We are looking at a force that helped shape the history of life. We are looking at the conductor of an orchestra that has been playing for billions of years, guiding the breeding of corals, the migration of birds, the movement of fish, and the evolution of our own ancestors. The tides are not just water moving, they are the heartbeat of the biosphere, and that heartbeat is driven by the moon. The moon was born from catastrophe, a giant impact between Earth and a Mars-sized body approximately 4.5 billion years ago. From the debris of that cataclysm, our moon was born. Mythologically, the moon held profound significance for every human culture. From Selene's love for Endymion to Chang'e's tragic exile, from Luna's role in Roman religion to Chandra's place in Hindu cosmology. Humans everywhere created stories to explain this mysterious celestial body. Apollo, god of the sun, represents the complement to lunar deities. The sun and moon, Apollo and Artemis, light and darkness. These pairs reflect fundamental astronomical realities about our place in the cosmos. Scientifically, the moon's gravity creates tides, not through magic or supernatural force, but through the elegant mathematics of differential gravitational forces. The moon pulls slightly harder on the near side of Earth than on the far side, and this difference, this differential, creates the tidal bulges that result in the rising and falling of the oceans. The sun also contributes to tides, creating the monthly cycle of spring and neap tides as the sun and moon align and misalign. The tides represent a massive transfer of energy, from the moon's orbital energy to heat in Earth's oceans and crust through friction. This energy dissipation slows Earth's rotation and causes the moon to recede from Earth at about 3.8 centimeters per year. The moon's tidal effects on Earth are so powerful that they've left geological and biological signatures. Organisms have evolved circatidal rhythms. Ancient rocks record tidal cycles. The entire history of life on Earth has unfolded against the backdrop of changing tides as the moon has slowly receded from Earth. What's remarkable is how the mythological and scientific perspectives complement each other. Ancient peoples, without sophisticated instruments or mathematical knowledge, observed the moon and the tides. They created myths to explain what they saw. These myths weren't wrong. They represented genuine attempts to make meaning of observed phenomena. Modern science provides the mechanism, the mathematical explanation for what the ancients observed. Science answers how, but mythology often addresses why in a deeper sense. Why does this matter? What does this mean about our place in the cosmos? The story of Chang'e, eternally separated from her beloved, speaks to something profound about existence, sacrifice, and transformation. The equations of Newton's law of gravitation describe the mechanisms, but they don't capture the poignancy that the myth conveys. Similarly, the story of Apollo and Artemis, the sun and moon, light and darkness, as twin siblings in eternal partnership, reflects an astronomical truth. These two bodies dominate our sky and create the fundamental rhythm of day and night. Myth and science are not opposites, they're different ways of understanding the same reality. Thank you for spending your time with me exploring the moon, its origin, its mythology, its role in driving the tides, and the remarkable science that explains how a celestial body so distant can have such profound effects on our world. Understanding the tides means understanding that we live in a dynamic, evolving system. The moon wasn't always where it is now. It won't stay where it is in the future. Earth's rotation isn't constant. The day-night cycle isn't permanent. Yet change doesn't mean instability. The tidal relationship between Earth and Moon has been extraordinarily stable over billions of years, stable enough for life to evolve and flourish. Life on Earth evolved within the context of Earth's current position relative to the Moon and Sun, the current day-night cycle, the current tidal range, the current length of the year and month. These have shaped life's diversity and complexity. Understanding this reminds us that life is not separate from the cosmos. We're not passive observers watching astronomical phenomena. We're embedded in these phenomena. The moon's gravity shapes our oceans. The sun's fusion creates the energy that powers most life. The rhythms of the cosmos are the rhythms of life. The study of tides connects Earth science to exoplanetology. When we look for potentially habitable exoplanets, we consider whether they might have moons like Earth's. We ask whether they might experience tidal heating that could warm oceans beneath their surface. We wonder whether their biological systems might have evolved circa tidal rhythms. The Earth-Moon system is a reminder that planetary systems are complex, dynamic, and profoundly interconnected. NASA's renewed focus on lunar exploration, the Artemis program, reflects renewed scientific interest in understanding the moon, not just as an astronomical object, but as a potential home for human settlement and scientific research. As we contemplate returning to the moon, establishing research stations, and potentially mining lunar resources, we do so with a deeper understanding of what the moon is, how it came to be, and how it continues to influence Earth. Despite all our knowledge, mystery remains. We still don't fully understand all aspects of tidal dissipation. We still have questions about the moon's formation and early history. We still discover new tidal phenomena and new ways the moon influences Earth. This is as it should be. Science doesn't eliminate mystery, rather it reveals deeper mysteries. Understanding how gravity works doesn't diminish the wonder of feeling gravity. Understanding the mechanism of tides doesn't make it less remarkable that the moon's gravity moves billions of tons of water twice every day. The moon remains our cosmic companion, mysterious, powerful, ancient, slowly changing. It remains worthy of our attention, our study, and our wonder. Thank you for spending your time with me exploring the moon, its origin, its mythology, its role in driving the tides, and the remarkable science that explains how a celestial body so distant can have such profound effects on our world. Download the free One Thing sheet from the description if you'd like to reflect on this night's learnings. What was the single most important insight from this documentary? What shifted in your understanding of the moon, the tides, or the Earth-Moon system? If you found this exploration valuable, please leave a comment below. Tell me what aspect of the moon or tides fascinated you most. What mysteries do you want explored further? What insights will stay with you? Your engagement builds our community and helps us reach more people interested in genuine understanding of our world. Like this video, subscribe to the channel, hit the notification bell so you never miss a new documentary. The story of the moon doesn't end with this episode. The moon's story continues as it recedes, as it influences Earth's oceans and rotation, as humans return to its surface and establish a presence there. The relationship between Earth and Moon, a relationship that began in catastrophe 4.5 billion years ago, continues to unfold. Thank you for being part of this exploration. Thank you for your curiosity. your willingness to engage deeply with complex ideas, and your openness to wonder at the cosmos. The moon awaits. It's been our companion for billions of years. It will continue to guide the tides, inspire our myths, and call us to explore and understand our place in the universe. Until next time, keep looking up.